And so we're going to finish up chapter 17, and then the lab, we have a problem right now with I had the Visual MinTech lab scheduled for today. I was going to break that up into two separate Visual MinTech labs, but something's wrong with the application, and so they're fixing it now, the computers. So we'll do that next week. Instead, what we're going to do today is we're going to take a look at the crystals and then continue with the report. And so if your crystals, what we want is we want big crystals. The bigger the better. But if your crystals, they're hard to see any individual crystals in there, then we're going to try another recrystallization. You know, trying another recrystallization is just dissolving all the crystals again and then just trying to get them to slowly crystallize out of solution. I'll talk more about that after we see what people's crystals look like. But we're going to just focus on buffers right now. One of the advantages of buffers is they resist pH changes. So one of the examples I did on Thursday on the video was I took 25 milliliters of water and then added 1 drop. 1 drop is about 0.05 milliliters. So 1 drop, 0.05 milliliters of, we'll try to keep this sig figs to 4. This is being too precise, but I don't want to worry about sig figs right now. 1 drop is 6 molar HCl. And so the water, if it's pure water, what does pure water start off as? What pH? 7. Actually, we can be more precise here. How many sig figs can I put on 7? At 25 degrees C. 2. So is that 2 sig figs? It's actually, for power functions, it's not. We need 1 more because power functions are the exponential term, looking at the exponential. And so the 7, it's 10 to the minus 7. In fact, let's take a look at power functions a little bit more. You know, whether it's pH or pKa. You know, for geologists, you usually think about the Richter scale. So if there's an earthquake that's magnitude 6 versus an earthquake that's magnitude 9, you know, how many times more powerful is a magnitude 9 earthquake over a magnitude 6 earthquake? Yeah, it's 3 powers. 3 powers of 10 would be 1,000 times more powerful. And so these power functions, the nice thing about power functions is they're very compact. If you look at how many characters are required for scientific notation, it's a lot versus to express this in terms of a power. This is our x. Here, actually, do I want to do that? Maybe I'll just type it in here. This is our x, and this is our px. Our x could be, you know, the hydronium concentration. It could be the Ka, it could be the Kb. Our px could be the pH, pOH, pKa, pKb, etc. And so a lot of tables like these power functions because they take less space. They take less space than, that's less paper. And less paper is, you know, better for resources. And so anyway, if we express it instead of scientific notation, if we express it as a power function, that's fine. That's good. But we have to recognize that the difference between an 8 and a 7 is a factor of 10, you know. And so when we compare 8 and 7, 7 would be 10 times less or 10 times more. This is kind of tricky because Richter scale is kind of different. You know, an 8 versus a 7, I'd rather be in a 7, you know, earthquake than an 8 earthquake. But here, which one's more? A 7. A 7. Because a 7 would be, as we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 10 to the minus 8. You know, I could try to put in 10 times 10 to the minus 8, but Excel is going to change that immediately. So if I go to 10, yeah, that's 10 times more than 1, right? But Excel is going to change it to what? It's going to change it to 1 times 10 to the minus 7. And so we're stuck. All right, what if I'm at 5? Let's say I'm halfway between 1 and 10. Shouldn't the power function be 7.5? And why isn't it 7.5? Because if I'm halfway between this in scientific notation, shouldn't I be halfway between it in power function? So this should be a 7.5. Is that right? No, it's not right, because this is a linear scale. However, power functions are, yeah. And so it doesn't quite go linearly, but what it does do is, if you're closer to 7, let's say in the high, above 5, let's say 5 times 10 to the minus 8, then it's going to be closer to 7. And if you're closer to 8, then here, it'll be in the lows, in the low. And so when we see this, I see, you know, the power function would be between 8, 7, and 8. And on one side it's closer to 7, the other side is closer to 8. All right, and so when we did this, did anybody have a chance to see the video? Nobody? Okay, this is kind of a review of it. You can take a look at the video for a more complete summary of what we did. So we're adding 6 molar HCl to water. The water is unbuffered. What's going to happen to the pH? I suspect the pH will change. How much will the pH change by? Well, let's go ahead and calculate how much the pH changes by. So what's our first step here? Solution dilution. So what's the dilution factor for HCl? So what I'm going to do is I'm just going to go 4 sig figs, 2 sig figs there. Maybe I'll make this 3 sig figs. So I'm going to say we'll go with 3 sig figs. I'll carry more. What's the dilution factor here? Well, it's a 0.05 to 25.05 dilution. And again, there's more sig figs there, but I don't want to write them all out because it just takes a long time. And the same thing, 6 molar to 3 sig figs. That's a pretty significant dilution. We're taking 5 parts and diluting it to 2,505 parts. And so we expect the concentration to change significantly. So we'll go 0.05 divided by 25.05 times 6. And it's no longer 6 molar, as you'd expect. It wouldn't be anywhere near 6 molar. It's going to be 0.01197 1197. 6, etc. molar. Well, the HCl is a strong electrolyte. Strong electrolyte is going to dissociate. And so what is the pH of this? The pH is just going to be the negative log of the H plus, or the hydronium concentration, which will be the negative log of, this is going to entirely dissociate into, and so I'm just going to take the log of my answer, negative log of my answer, and I get a pH of 1.92. 1. So the pH started at 7 and ends up at 1.92. Did the pH change significantly? Yes. Like how many times did it change? Now it used to be not acidic, but now it's acidic. How many times more acidic is it? Just roughly. Well, it's going to be 5 powers of roughly. 5 powers more acidic. 500,000 times. And so this is 500,000 times more acidic than what we started with. And so this is unbuffered. The purpose of a buffer is to prevent pH swings, you know. Like, for example, your blood is buffered by 2 different buffer systems, but, you know, if your blood pH swings significantly, that's lethal. So your blood pH is like 7.2. Is it okay to go up to 7.5? What do you think? Or down to 6.9? No. There's some serious problem if your blood pH is like that, but we can see, you know, if a drop of maybe stomach acid, I don't know what the molarity of that is, but, you know, gets into your blood, you know, what can happen? Well, let's take a look at a buffer. Now, our buffer, we want to make a buffer that's pH 7.00. How about acetic acid, acetate? Will that work? And so does anybody recall buffer range? What buffer range is? Mm-hmm.
Are you talking about the ratio of buffer, the base to acid for a buffer?
Yeah, right. Exactly. It's base to acid, you're right. And so I should have written this acetate acetic acid because we have the base on top, the acid on the bottom in the Henderson-Hasselbalch equation. So is this a viable buffer? Well, we had something called the optimum pH. Did I talk about the optimum pH? The optimum pH of a buffer is when we have a base to acid ratio of 1 to 1. That happens at what we call the half equivalence point of a titration. At the half equivalence point, what is the pH equal to? pH is equal to pKa. And so the pKa of this buffer system here is equal to 4.74. And that's when we have a 1 to 1 base to acid ratio. 1 part of base to 1 part of acid. This is called the optimum pH here. It's optimum because we have equal amounts of base and acid. But sometimes that pH isn't so great. Do you want to make a buffer that's pH 474? Maybe not. Maybe your preference is to make a buffer that's pH 4 or a buffer that's pH 5, but not 474. Well, our preference is to make a buffer that's pH 7.00. Is this going to be a good system for that? And so if we're trying to make a pH 7.00 buffer from this system, it's not good. Because the buffer range for this system is going to be between 374 to 574. So we go from the pKa, which is 474, plus 1. This would be pKa plus 1. Down to the pKa minus 1. Now, if you recall from the Henderson-Hasselbalch equation, if we had a pKa plus 1, what is our log of the ratio? Our log of a ratio is 1. how can we get a log of the ratio to equal 1? How we can get it is if we had a 10 to 1 base to acid ratio. And so if we had 10 parts of base for every 1 part of acid, that's log base 10 of 10, which is just equal to 1. And down here, how do we get a minus 1? How we get a minus 1 is if we have a 1 to 10 ratio of base to acid. And so this would be 1 part of base, 10 parts of acid. But if you want to go up to pH 7, so this would be about 6. If we go to 7, that would be 1 more power. And so this would be closer to what? So for example, 574 to 674 would mean that we would be at pKa plus 2. If we're at pKa plus 2, what is the base to acid ratio? 100 to 1. And now we got to go a little bit beyond that because we want a pH of 7. So if we want a pH of 7, that means we have to have more than 100 parts of base to every 1 part of acid. Is that a very balanced base acid ratio? No, it's not. It's lopsided. It's heavily biased towards base. That means the acid concentration has to be 100 times smaller. If the acid concentration has to be 100 times smaller, then you probably have to make it highly concentrated. Otherwise, it's not going to have something called capacity. And so we don't want the buffer to become too lopsided. This is what we call lopsided over here. This is too much base. Likewise, if we go down to 274, it's a 1 to 100 ratio. If we go to 174, it's a 1 to 1,000 ratio. You know, and so it's going to be too lopsided. This is heavily biased towards acid. This is heavily biased towards base. Ideally, we would like a 1 to 1 ratio, but sometimes that's not the desired pH. And so this would be okay to make a buffer of pH 4. That's within the range. And this would be okay to make a buffer of pH 5, but not 6, and not 2, and certainly not 7. Okay with that? So I'm going to give up on acetic acid because the pKa of acetic acid is 474. And so what we need to do is we need to find another acid, weak acid. So I see this acetic acid is 1.8 times 10 to the minus 5. So the pKa is between what and what? The pKa is between 5 and we go from 1 to 10. 10 times 10 to the minus 5 is 1 times 10 to the minus 4. And so the pKa for this is between 4 and 5, but closer to 5 because we're, because to be closer to 4, we need to be above 5 times 10 to the minus 5. So this is not good. How about this one here? Hey, wait a minute. Look at this one. 1.0 times 10 to the minus 7. What's the pKa of that? 7.00. This is perfect. Because if we use this acid and the base would be arsenate, then we could just mix those in a 1 to 1 ratio and the optimum pH would be the buffer pH. And so it's a nicely balanced buffer. The problem with arsenic is it's pretty poisonous, yeah. This is toxic. So we don't want to handle arsenic. Let's find something else. How about arsenous acid? If I look at arsenous acid, that has going to be a pKa between what and what? 9 and 10, but closer to what?
9.
9, exactly. So this is, yeah, that's too far, isn't that? Too far. Do you see? Okay, here's one. Carbonic acid, 4.4 times 10 to the minus 7. This one's closer to 7. This is pretty good. But there's a problem with carbonic acid. The problem with carbonic acid is it's unstable and decomposes into CO2 and water. And to make a carbonic acid solution, you have to bubble CO2 in there. And that's very hard to control the concentration. We need to control the concentration to make a buffer. Bicarbonate's no problem. Oh, is this bicarbonate? No, that's carbonic acid. Bicarbonate would be no problem, but carbonic is not good. Do you see anything else? How about this? Monohydrogen citrate. Does that look good? This has a pKa close to 7. This would be good. But the problem with citric acid is it's a pretty good reducing agent. And so it's decomposed easily. It's easily oxidized. You know, citric acid, like fruits and that kind of stuff, are pretty easily oxidized. So this stuff decomposes. Let's stay away from that. Cyanic, that's too far away, too far away, too far away. Oh, this is good. Hydrosulfuric acid. Would you use that? That's right on. Right? Perfect. 1 to 1. This would be perfect. Except there are multiple problems with H2S. Can you think of some problems with H2S? Probably the biggest one is H2S gas is toxic at the part per billion level. H2S gas, fortunately you can smell it at the part per billion level. It smells like rotten eggs. But soon it desensitizes your nose, so you can't smell it anymore. And so it's best to stay away. Not only that, H2S isn't very soluble. Solubility is only 0.10.
So, question. You said it was toxic for parts per billion, but you said like we smell it in eggs. So, when we smell it in eggs, is that less than part per billion? Or?
You can detect it at the part per billion level, but the thing is you aren't continually exposing yourself to it. If you're exposing yourself continuously at the part per billion level, it would be lethal, I think, eventually. Maybe this, hypochlorous acid. Hypochlorous acid is between 7 and 8, closer to 8. This could work. But hypochlorous acid is bleach. Not sure if you want to work with bleach. What else? Oh, here, this might work, but this is closer to 6. This would be hydrogen malonate ion. Possibility. See any others? Hydrogen phosphate. Which one? Dihydrogen phosphate. Yeah, dihydrogen phosphate, this is going to be between 7 and 8, but closer to 7. So this is looking good, dihydrogen phosphate. The nice thing about phosphate is it's common, used in detergents, soaps, etc. What other choices do we have?
Hydrogen phosphide.
This one?
No, a little bit above.
Oh yeah, dihydrogen phosphide. This is good too. This is a good one. Except the problem with dihydrogen phosphide is phosphorus acid. Is it very common? No. Phosphoric acid, yes. Phosphorus, no. Pyrophosphoric acid, not very common, but this would work too. 2.5 times 10 to the minus 7. Any others? This could potentially work. However, this succinic acid is decomposes, electron rich. Thiophenol. Thiophenol is one of the chemical compounds that I think gives skunks their odor, and so it smells really bad. Although this is really close, you wouldn't want to use this stuff. So we're going to pick which one? We're going to pick dihydrogen phosphate. And so that's what I did on Thursday. Dihydrogen phosphate. Let's calculate the Ka value for that. The Ka for dihydrogen phosphate, 6.3 times 10 to the minus 8. So I'm going to just change this one here to 6.3 times 10 to the minus 8. Let's expand this out a little bit. I don't want to round this right just yet. So we'll just go with 7.20 for dihydrogen phosphate. This would be the acid. What would the base be? Monohydrogen phosphate, good. But the problem is if we had a one-to-one mixture of dihydrogen and monohydrogen, the pH would be 7.20. So what we need is a little bit more acid or base. We need a little bit more acid to bring the pH down. And so what we do is we got to figure out how much, what is that ratio of base to acid that we need. And the way we do that is by using the Henderson-Hasselbalch equation. That is, the pH is equal to the pKa of the acid, in this case it's dihydrogen phosphate, plus the log of the base to acid. The base is monohydrogen phosphate, and the acid is dihydrogen phosphate. So the desired pH is, we want a pH of 7.00, so we're going to have to adjust the ratio because our pK is a little bit too high, and so we'll get this log of the ratio. And then we're going to get minus 0.20 if I subtract 7.20 from both sides is equal to the log of this ratio. And then the ratio of base HPO4 2 minus to acid H2PO4 minus is equal to 10 to the minus 0.20. This is a power function, so I'm allowed 2 sig figs out here, but I'm going to carry more. Point 6309. carry some extra digits. And so in other words, this is going to be 0.63092 ratio. So I need 0.63 parts of base for every 1 part of acid. So a little bit more acid to bring the pH down to 7. I'm going to invert this ratio. If I invert that ratio, then what I'm going to get is this. I'm going to need, for every 1 part of base, I'll need 1.584 parts of acid. And so 1 molar base to 1.58 molar acid. This will work. And so just anything that has the same ratio is fine. And so what I can do is I can make this, I'll talk about buffer capacity now. Uh-huh.
Scroll up a tiny bit, please.
Yeah, okay. I just changed it because this 0.63, I just want them both 1. You know, this is more sig figs here. I'm not writing it. It should be like 1.0 something. But let's talk about buffer capacity. So, if I keep the ratio the same, then the pH shouldn't change. So let's say I went from 100 over 158, you know, to 0.000 100 over 0.000 158. Will the pH change? Now, the pH will stay the same, although if I keep diluting it, if I dilute it more, this is concentrated, this is diluted. If I keep diluting it, eventually all buffers, regardless of what their pH is, I could have a pH 4 buffer, but if I keep diluting it and diluting it, at infinite dilution, its pH should approach that of pure water because there's so little buffer in there. It's practically just pure water. And so I have to be careful about overly diluting it. In this case, it's not going to make any difference because it's a pH 7 buffer. But eventually it'll be so weak, it's like pure water, and it will be unbuffered. And so this is buffer capacity. Over here we have high capacity. Over here we have low capacity. So when you're making buffers, you kind of have a choice of how concentrated you want. The more concentrated, the more expensive it's going to be because you have to use more chemicals. And you purchase the chemicals by how many grams you desire. And so this is going to be a much more expensive buffer than this for equal volumes. In fact, which buffer would you rather have? You'd rather have the one with higher capacity. But there's a problem though. This capacity is kind of ridiculous. Can you make 158 molar salt solution? Is that even possible? Probably not possible. This is probably too high. It probably exceeds the solubility. So you might think, okay, I want the most concentrated acid I can make, you know. You might try to make the most concentrated acid and then you find out, well, you're kind of stuck, you know. What's the most concentrated HCl you can have? It's actually less than that, less than 12. It's 12 molar. That's the most concentrated, a little over 12, maybe closer to 13, but that's it. There you go, I don't want 12, I want 20. or 30 molar. I'm going to be doing some heavy reactions. Or nitric acid. And so there are limits to this. And so this is too high. So what we'll probably do is we'll just back it down. Actually, maybe not go up by a full factor of 10. Let's try something like, let's double it. How about that? We'll go with 2 molar and 158. I'm just going to times 2. I carried all the digits in the calculator, so this might be off from your calculation. 3.169. 7 molar. So if I go 2 molar base, which is HPO4 2 minus, and 3.1697 molar acid, which is going to be H2PO4 minus, that would work. This is still going to have a much higher capacity than this. This is highly dilute. So we'll use these as 2 examples. One high capacity buffer and one low capacity buffer here. All right, so the first calculation we're going to do is 1 drop of 6 molar HCl to our high capacity buffer. So what I'm going to do is do the same thing. I'm going to take the same, actually it depends. What volume of buffer should I use? Does it matter? Well, to be fair, I should use the same amount as I did for water. How much water did I use here? I used 25 milliliters of water and added 1 drop of 6 molar HCl. So what I'm going to do down here is I'm going to take 25 milliliters of the high capacity buffer. This is to more sig figs. Because the capacity is going to depend on 2 things. One, it's going to depend on the concentration. And 2, it's going to depend on the volume. You know, if you add 1 drop of HCl, not to 25 milliliters of water, but let's say you added 1 drop of 6 molar HCl into the ocean, are you going to see a significant pH change? No. And so buffer capacity is 2 things. 1 is concentration, and 2, it's volume. Large volume will have high capacity. Small volume will have low capacity. And essentially what it boils down to is how many moles of buffer component, how many grams of stuff do you have dissolved in there? If you have a lot of stuff dissolved in there, it's going to be high capacity. A little bit's low capacity. So to be fair, I'm not going to put like 5,000. Here if I have 5 milliliters of buffer and I'm adding 1 drop, that's hugely different than if I have 5 liters of buffer and adding 1 drop. 5 liters. Oops, I have this backwards. 5 liters is much higher. Capacity then. Five milliliters, even though the concentration is the same. So to be fair, we're going to start off with 25 milliliters of the high capacity buffer and add 1 drop. When we do that, we have our initial step, which is always in chapter 17. We do this, which is the solution dilution step. And then take a look. The HCl is going to have the same dilution factor, 0.05 over 25.05. of 6 molar, which is 0.0. $11.97.6. This is the same dilution as before. 11.97.6. So that was significantly diluted. Let's take a look at the acid component here, H2PO4 minus. That's going to be in the buffer here, this 25 milliliters. So we're taking our original 25 and diluting it to 25.05. Is that a significant dilution? Is that really that significant? No, it's not, but we're going to calculate it anyway because even though it's a slight change, I want to know how much. And so the acid component, we had a little bit more, 3.1697. 3.1697 molar. I'm going to carry some extra digits here. And so I have a times 25 divided by 25.05. And I go through 3.1634. So I went from 1697 to 1634. Was that a big dilution? Not really when you think of it as being, 3,000 or 30,000, 31,697. It's not a huge dilution, but we'll factor it in. For the base, HPO4 2 minus, what's the dilution factor? Forget it. Let's save it right now. Do you have the dilution factor? It's the same because the acid and base are in the same solution here. It's a buffer solution. The concentration's different though. 2 molar for the base. And so that's 25 divided by 25.05 times 2. .996 0 molar. So we went from 2 molar to 1.996 molar. When we round that to the correct number of sig figs, there's not really much change. But I'm going to leave it with some extra digits there to avoid rounding error. All right, so now I have this. What's going to happen next? So take a look at this and tell me what's going to happen next. I'll try to save this. All right, so I want to figure out what the pH change is. So what's the next step after step I?
Strongest acids, strongest base.
Yes, that's what I was looking for. So what's the strongest acid? HCl. And the strongest base? Which one?
Monohydrogen phosphate.
Yeah, monohydrogen phosphate. And this is going to produce chloride and dihydrogen phosphate. What's K for this reaction?
Very large.
Mm-hmm. Very, very large. Very large is with a strong acid and water. Monohydrogen phosphate's a better base than water. And so we'll call it very, very large. What's the initial HCl? (0.011976 molar). What's the initial concentration of monohydrogen phosphate? (1.996). Chloride 0. Dihydrogen phosphate is 3.1634. Now, does this buffer have enough capacity to neutralize the HCl? And the answer is yes. Because HCl is a limiting reagent, and so we're going to lose all of it. The monohydrogen phosphate, that's our excess reagent. And so the limiting reagent gets completely consumed. And we've lost a little bit of base. How much base have we lost? 0.011976. Minus 0.011976. And yeah, we lost a little bit of base, 1.984. So we went from 1.996 to 1.984. Was that really significant? Not really. I mean, yeah, we did lose a little bit. And so it changed. And then we're going to gain some chloride. So we're going to get 0.011976 molar chloride. And we're going to gain some dihydrogen phosphate, 0.011976 molar here. So I'll calculate that. 3.1634 plus 0.011976. 3.17. 5376. So what we're curious about is this. One, there's no more HCl there, and so we've neutralized the strong acid. This buffer had enough capacity to do that. But did this buffer have enough capacity to maintain the pH? And so what we see is this is our HH buffer. And so let's calculate the new pH of this. And the ratios were changed a little bit. And so this is pH is equal to pKa 7.20 plus the log of the base to acid ratio. The base is 1.984. The acid is 3.175376. I don't really need to carry that many digits, but it's my calculator. So flip that times 1.984. And then take the log of that, and I get minus 0.204. Plus 7.2. And I get a pH of 6.9957. Okay, then I'm going to round this to 2 sig figs. My pKa was only good to 2 sig figs. Rounding this to 2 sig figs, I'm going to get 7.00. So did the pH change significantly? No. Negligible change. So in this case, the buffer did its job. It had enough capacity to neutralize that added acid. However, you can see as the numbers grow smaller, then that one drop is going to be more significant. And so as these concentrations shrink, the impact is going to be larger. All right, let's try the low capacity. In fact, Um, we'll start off with the same amount, 25 milliliters of this, and then we're going to add 1 drop. The initial concentrations of this were 0.001 100 molar and 0.000158 molar. I think that was it. We'll just go with those. Yeah. 0.00100 and 0.00158. Okay, this was the base. This is the acid. Okay, then I'm going to go up to 25.05 milliliters. And let's calculate the HCl. The HCl has the same dilution factor, 0.05 to 25.05 of 6 molar, which came out to 0.01197 molar, 1197, as I recall, 1197.6. And now we have the, we'll do the base since it was on top over here, HPO4, 2 minus. This is going to be a 25 to 25.05 dilution of 0.000 100 molar. Comes out to 0.400 molar. Okay, that's the base. So we went from 100 to 99.8, basically. And then the H2PO4 minus also had the same dilution factor, 25 to 25.05, 0.000158 molar. So it's 25 divided by 25.05 times 0.000158. That gives us 0.000156. So we went from 158 to 157.6, so barely changed there. So these are very mild dilutions, the last two, but I'm going to factor those in. Okay, after I do this, then what do? Take the strongest acid, HCl, plus the strongest base. In this case, the strongest base is the monohydrogen phosphate. And this is going to make chloride and dihydrogen phosphate. The initial HCl is 0.01197, 6. The initial monohydrogen phosphate is .0000998. Just go with that, molar. Chloride 0 molar. Dihydrogen phosphate is 0.0001576 molar. So now, when we look at which one of these is the limiting reagent,
HPO4.
yeah, this is the limiting reagent. We don't want the buffer to be the limiting reagent. If the buffer is the limiting reagent, then what we say is the capacity of the buffer has been exceeded. We don't have enough buffer to neutralize it. If we don't have enough buffer to neutralize it, or the capacity can be exceeded too if there's a more dramatic change in the ratio. As well. But in this case, the limiting reagent is going to be completely consumed. So the change should be complete. And let's take a look at what we have at the end. At the end of this, we have no more base component, 0 molar. And then we're going to lose some HCl. So we're going to start off with 0.01197.6 minus point quadruple 0.998. 0.01197.6 minus point quadruple 0.998. You get 0.01187.62 molar. Chloride's going to grow by point quadruple 0.998. And H2PO4 minus is going to grow by that too. So this is going to be plus point quadruple 0.998 molar. And so I'll have point triple 0.1576 plus quadruple 0.998. And it's going to give me triple 0.2574 molar. So the type of solution I end up with here is strong acid, weak acid. Well, actually, this is amphoteric. So really we should solve this using simultaneous, but we're going to assume that very little hydronium comes from the amphoteric, and most of the hydronium comes from HCl. So just assume nearly all HCl, nearly all hydronium from HCl. Therefore, the pH is equal to the negative log of 0.0118762 0.0118762 and I get a pH of 1.925. We'll round this to 2 sig figs. pH is going to be 1.93. So here we went from pH 7 to a pH of 1.93. Was there a significant change? Yeah. And so we shouldn't exceed the capacity, so we have to make sure that we have enough buffering capacity. Another thing we could have tried is just use a larger volume. So rather than 25 milliliters, if we use 25 liters, then we wouldn't have as much impact, because the solution dilution of the HCl would have diluted it significantly.
Listen, going down to calculation for the pH, would the pKa be included in it?
No,
Why?
because it's no longer a buffer.
Once it's exceeded the buffer capacity, it's just not included in calculation anymore?
Well, we have two. So, for example, HCl. HCl is a great acid. HCl would make a great acid in a buffer to neutralize bases. So, if we're adding base, the HCl would clean it up. You know, just mop it up. But the problem is its conjugate, chloride. Is chloride a very good base? Excuse me. No, so would chloride just mop up all the acid? The buffer has to be versatile in the sense that we're going to have an acid component that will neutralize added base, and we'll have a base component that will neutralize added acid. So this one's great for added base, but it won't do anything for added acid. And so this is not a buffer. And so we have HCl and its conjugate base, chloride, but it's not a buffer. We do have a buffer, though. The buffer would be monohydrogen phosphate with dihydrogen phosphate. But this is terribly lopsided because when we look at how much of each we have present, how much of the monohydrogen phosphate do we have? We have zero. We have nothing. If we have no base component, then it's going to be worthless for added acids. However, we have plenty of acid here, so if we add base, it shouldn't be a problem, although this is amphoteric, so it's trickier. But does that kind of make sense? It's because we're missing a monohydrogen phosphate. We don't have any, and we need both for a buffer, you know, for this buffer system at least. Amphoterics are kind of like buffers. Okay, the last part of chapter 17 I wanted to talk about was indicators. I talked about amphoterics being like buffers, didn't I? Amphoterics has a Ka and a Kb. And so if we have an amphoteric like this, it's trickier because it has to be solved simultaneously. So that makes it tricky. We could solve this. You know, this is kind of complicated. If I didn't assume this, assume nearly all hydronium from HCl, then I would have had to solve this simultaneously because I have HCl, which is going to supply a lot of hydronium, but I also have dihydrogen phosphate, which could also supply hydronium. And the problem is dihydrogen phosphate can also produce hydroxide. And the Ka for dihydronium phosphate and the Kb for dihydronium phosphate describe two different equilibria. Unlike in an HH buffer. In an HH buffer, the Ka for the acid component describes the same equilibrium as the Kb for the base component. Did I already talk about amphoterics? You talk about it over here. H2PO4 minus can do a Ka, that is H2PO4 minus plus water yields H3O plus plus HPO4 2 minus. And H2PO4 minus can do a Kb collision. In a Kb collision, we take our H2PO4 minus plus water, but in this case, water took it. In this case, dihydrogen phosphate takes to make phosphoric acid and hydroxide. When you look at these two equilibria, they describe different equilibria. This top one is the equilibrium between dihydrogen phosphate and monohydrogen phosphate. The second one is between dihydrogen phosphate and phosphoric acid. So they're describing two different equilibria. These two equilibria are unique. And then they're going to be tied together with Kw. And so these two are not equal. This is what this is supposed to say, not equal. But we will need Kw here because we need to tie hydronium with hydroxide. And there's a seesaw relationship between those two. It's shown by Kw. Versus an HH buffer. In an HH buffer, we have the acid component, H2PO4 minus. This is just going to have a Ka. The Ka is going to be H2PO4 minus plus water, which yields H3O plus plus monohydrogen phosphate. And then we have the base component of the buffer, which is going to be HPO4 2 minus. It's going to be our Kb. Both of these are amphoteric, but it's going to happen as well. And so the H2PO4 minus plus the H2O liquid is going to form H3PO4. Oh, actually, no, what am I doing? H2. This should be HPO4 2 minus, sorry. HPO4 2 minus plus water is going to form H2PO4 minus plus hydroxide. When I look at these two equilibria, this is the equilibria between H2PO4 minus and HPO4 2 minus. When I look at this one, this is the equilibrium between HPO4 2 minus and H2PO4 minus. So both of these describe the same equilibrium. And therefore, we could use the HH equation. If we only had the amphoteric alone, without the HCl, so if only amphoteric, then the simultaneous simplifies into the pH is equal to pKa for the amphoteric plus the pKa. It's getting crowded there. Let me write this over here. Normally simultaneous is very difficult, but since both the since both the acid and the base are the same species, then it simplifies things. And so we have three scenarios. The acid and the base are the same thing. That's the top one, where we do simultaneous. Versus the Henderson-Hasselbalch, where the acid and base are conjugates. Versus the third scenario is when the acid and base are not related. See if I can save this. Can't. So the acid and the base are conjugates. The acid and the base are the same species. And the third scenario is when the acid and the base are unrelated. when the acid and base are unrelated, we have to do simultaneous. There's no way around it. When the acid and base are the same thing, then we also have to do simultaneous. But somebody's done all the math for you. So this simultaneous simplifies into a very simple equation, and that is the pH of an amphoteric solution is equal to the pKa for the amphoteric plus the log, oops, no, not plus the log, sorry, pKa for the amphoteric plus the pKa for the conjugate acid of the amphoteric divided by 2. So it's a fairly simple equation, but the acid and the base have to be the same species for this to work. There are other restrictions too. It has to be, the simplifying assumption has to work, etc. So here what I did was we have a strong acid and then we have this simultaneous. So I have to do this simultaneous, but we're going to assume that the dihydrogen phosphate is not going to contribute much additional hydronium, and therefore we get this. All right, the last topic I wanted to talk about, buffers. Buffers are weak acid and weak base, or weak base. And these have to be conjugates. The weak acid has to have a different color than the weak base. And so we should see two colors. One color for the acid, one color for the base. So normally when you put in phenolphthalein, the acid color is colorless. The base color is red. And so what happens is you have phenolphthalein. This pH just stands for the anion of phenolphthalein, so this is just a shorthand way of representing it. It's colorless. And so you put a couple of drops, or a drop, into your Erlenmeyer flask. And it stays colorless because there's acid in your Erlenmeyer flask. And then you start adding sodium hydroxide. What's going to happen? Well, the sodium hydroxide is going to attack the strongest acid present, which could be the indicator, or could be the other one, but anyway, the acid will eventually attack the indicator. When the acid attacks the indicator, or not the acid, this is acid. When the base attacks the indicator, like sodium hydroxide, then that's going to convert my acid into sodium phenolphthalein 8 in water. So when we have a strong base, it's the same thing. K for this would be very, very large. So as we start neutralizing our acid indicator, which is colorless, it's going to convert it into our base indicator, which is red. So initially we start off as colorless, but we'll add the sodium hydroxide and then convert that into the base form. The base color is red. And when we look at it, if the sodium hydroxide is the limiting reagent, Lr, then we're going to end up with a mixture of weak acid and weak base, which are conjugates. In other words, we're going to end up with a HH buffer. And so indicators are like buffer solutions. And we do the same type of thing. We usually look at it in terms of the pH here. If the pH is equal to pKa minus 1 versus the pKa plus 1 versus just the pKa, here, this will give us an indication of the color. So a plus 1 means that we have a log of 10. And so this is a 10-to-1 ratio base to acid. Over here, a minus 1 means we have a 1-to-10 ratio of base to acid. And a pKa here just means we have a 1-to-1 ratio of base to acid. Now, in order to visually see it, the color stand out, we need at least a 10-to-1 ratio. And so solutions from pKa plus 1 on are going to be red. And so we could go to pKa plus 2, which would be 100-to-1, or pKa plus 3, which would be 1,000-to-1, etc. On the other hand, if we have a pKa minus 1 and smaller, like a pKa minus 2, etc., this would be a 1-to-100, or pKa minus 3, which would be a 1-to-1,000. We're going to see that the colorless form is going to dominate. So we have 1,000 parts more acid than base, and so this will be colorless. It's just when we get to 50-50. When we're at 50-50, then we expect intermediate color. And so between a pKa minus 1 and a pKa plus 1, we have an intermediate color. In this case, it would just be light pink. And so we could take a look at some indicators here. Like bromethymol blue. Bromethymol blue has a pKa. They're just saying pK for the indicator acid, HIN. IN just stands for some generic indicator anion. Is 7.1. So at a pH of 6.1 and lower, it's yellow because we're going to have at least at least 10 parts acid. At 5.1, it would be 100 parts acid. At 4.1, it'd be 1,000 parts acid. And then up here, at 8.1, we'll have 10 parts of base. Base color will dominate. At 9.1, 100 parts base, etc. And between 6.1 and 8.1, we're going to have green, intermediate color in this range. So we can see some indicators here. There's a wide variety of indicators. So if we're looking at alizarin yellow stays yellow from all the way here until we get to about 1 unit close to its pKa. pKa is around 11, so around 10 it starts to transition. And it's going to go through the transition until we hit about 12. And stays violent. And then 13, 14 will be violent, so on. Here, this might be a tough color to see. This would be okay. You're going from colorless to colored. Phenolphthaleins are the one we usually use, around 9, etc. But there's a wide range of indicators, starting off here, going up here, from low pH to high pH. And so we'll have stronger acids to very weak acids up there. The indicator, it doesn't have to be perfect. So for example, the equivalence point of this titration is pH 7. And so a perfect indicator would be bromethymol blue, which at 7.1 should be intermediate, and in that range it should be green. From 6.1 to 8.1 should be green. Because yellow and blue make green. But the problem is sometimes it's hard to see that transition. You know, is that a green, or is that a yellow green, or is that a blue yellow or yellow blue? And so it's hard to pinpoint that color. Versus phenolphthalein. Phenolphthalein just goes colorless to pink. You want it light pink. You don't want it red, because it just stays red from pH 11 on, basically. And so we want to hit it in this transition. But if we hit in this transition, we've missed the equivalence point. But when we look at the volume here, we're going from 25 to 25 point, maybe not even 0.05. 0.05 would be a drop. This is probably less than 0.05 error. So if we stop the titration here and then look how much we went across in milliliters of titrant, it's a negligible error. Not only that, when we do titrations, we usually calibrate or standardize the solution using phenolphthalein, and so that leads to a systematic error, and that systematic error is canceled out. We don't really worry too much about it. Whereas if we use alizarin yellow is going to transition around pH 11. And so if you catch it early, alizarin yellow, you catch it early, like here, tail end, and then, or you catch it late up here, there's a huge error. And so it starts kind of changing color here and then kind of ends here. Whereas here it starts changing color here and kind of ends there. And so this is going to lead to a huge error. Same thing with this. You know, it starts turning about here and then stops here. That's a huge horizontal uncertainty there. But any of these indicators should work okay. And bromethymol blue would be perfect for this. It's just hard to detect. We have less or fewer choices for weak acids. Reason is weak acids, they don't have that strong vertical rise. We're starting at a higher pH, and so the vertical rise isn't as great. Weak acids, the initial pH is kind of high. And so if we use bromethymol blue, you know, it starts transitioning to green around 6 and stops around 8. And so if we start transitioning around 6, we start here and end over here. And so that's a huge spread. And so bromethymol blue wouldn't work here because the pH of the equivalence point is above 7. And so, in fact, phenolphthalein would work well here. So phenolphthalein is a pretty versatile one. We could use this for weak acids. We could use it for strong acids. It works well. But most of the others are limited in terms of what you could use. All right, so that's indicators, and the color just extends. They just show a short bar here because they don't want to draw the yellow all the way to the top and the orange all the way to the bottom. And so it just extends. Acid color, transition, base color. All right, there are some other types of titrations that we deal with. So one thing is we might just flip it here. So rather than putting the base in the burette, we put the acid. And so now we're going to titrate it with strong acid, and this is going to be a strong base. So it's just inverted. So strong base, high pH initially, neutralize that using strong acid as your titrant. The same thing, we could start with a weak acid in the burette and the strong base in the flask. And so it'll just be an inverted weak acid base titration curve. You have that. Finally, we could have one more titration. And the last titration is going to be weak acid. Weak base. Weak acid, weak base, we need to do this simultaneous. Let's look at an example of weak acid, weak base. So for example, if we did acetic acid plus sodium fluoride, what would this produce? Well, this would produce sodium acetate and hydrofluoric acid. What's K for this? We could probably figure what K is by adding equations. So for example, if we did the Ka equation for acetic acid and the Kb equation for fluoride and then combine those with Kw, that could work. And so we need to determine that. It is not very large. It is not large. And so we're going to have an equilibrium. Since it's not large, it's not going to completely neutralize one or both the reactants. All right, now how do we figure out the pH? Well, this is going to be a Ka, this is going to be a Kb, this is going to be a Kb, this is going to be a Ka. What do we do here? Well, the Kb for fluoride and the Ka for HF, these are related. And the same thing, these are related too. They're conjugates of one another. So do we do two Henderson-Hasselbalchs? No, we don't. What we have to do is we have to do this simultaneous. Well, that's a big pain because we're going to have three equations. We're going to have Ka, we're going to have Kb, and we're going to have Kw. And what do you think is harder, the simultaneous with two equilibria or simultaneous with three equilibria? Simultaneous with three equilibria. What if we have more than three equilibria? Well, if we have more equilibria, it's just going to get progressively harder. So what are you going to do? Were you able to do simultaneous with two equilibria, or did you guys give up? I know some of you did it, but most of you pursued it a little bit and then maybe decided it wasn't worth it, right? And so if we have simultaneous with three equilibria, what are we to do? Well, I guess we could just give up at this point, right? Because maybe the math is going to be too horrendous. But we don't have to give up because there's something that's free. It's one of the best parts. It's free, and it's called Visual Mintech. Visual Mintech is great because they use activities. Remember, we don't use activities. We make an assumption that we don't have to worry about activities. We're trying to keep the concentrations low enough to not worry about it. And the other nice thing is they solve all these multiple equilibria, no matter how many there are, simultaneously. So you could have 3, you could have 4, 5, whatever. It's going to solve it simultaneous. And so today we're supposed to go into the computer lab and do this. But it's not working right now. And so instead, what we're going to do is what I was saying earlier. What we're going to do is we're going to check our crystals. You're going to look, do you have good crystals? You want big crystals. Why do you want big crystals? Not necessarily higher yield. Sometimes big crystals and nice crystals means lower yield. Sometimes you sacrifice some of the yield to get nice big crystals. In other words, we lose some of it. Purity. All right, take a look at this crystal here. Although you can't see the crystal facets, you know what that is? That's one gigantic silicon crystal. That's one single crystal. And why do they want a single crystal? They want a single crystal of silicon because of purity. Because when they cut this, they can cut it into wafers and not have to worry about purities. If there are impurities in there and they're making a, let's say, a silicon chip, you know, you're going to have a defect in there that's going to cause a failure. And so any imperfections will mean that they have to throw away that chip. And so the highest purity that they're going to get is a single crystal, because the single crystal is going to lock out impurities. So it's really interesting watching something like this grow. They recrystallize it, recrystallize it, recrystallize it, and this crust of impurities comes off, you know, this. And so, you know, the situation with our crystals is somebody's going to ask you, you know, how pure is your product? And you say, it's very pure. But how can you prove that your product is very pure? One way you can prove that your product is very pure is if you have very nice crystals. If you have very nice, well-formed crystals, then nobody's going to argue. They're going to see those crystals, although you can't really tell with this because you don't see the crystal facets, you know, the faces. But like quartz crystal, it's easy to see. So if you have like a quartz crystal like this, you know, you can't have too many impurities messing it up, otherwise it's not going to grow like that. You know, there'll be kink in the structure, and that kink will result in the crystal not growing to this size. I'm not saying grow crystals this big. You know, it'd be nice to grow crystals this big, then you can say that this is high purity stuff, because in order to get crystals this big, it's got to be pretty pure, right? Otherwise, impurities get in there and screw it up, and you get lots of little crystals. And so what we want are bigger crystals so that we can say, hey, you know, our product is of high purity. I don't know how many nines that would be, but it's of high purity. So we'll take a look at our crystals and see, do you have nicely formed crystals? If not, and it looks like just some kind of powdered solid at the bottom, then we'll want to do another recrystallization. If we do another recrystallization, what you want to do is you want to dissolve all your crystals. We can either dissolve them in hot water, or we can dissolve in room temperature. But what you want to do is you want to dissolve it so that all the crystals are dissolved, but you're right at that limit where it's, you know, as some of the water evaporates, it'll start to crystallize again. You don't want too much water in there. If there's too much water, then nothing crystallizes out. If you have too little water, you don't want that either, because if you have too little water, then too much crystallizes out. And if too much crystallizes out too fast, you get lots of tiny crystals. Lots of tiny crystals, you aren't going to be able to see that the crystals all look uniform. You know, how can you tell if you have a bunch of crushed sand versus one of these crystals? You know, this one looks pure, but if you have a handful of white powder, does that look pure? I mean, it may look pure, but how can you prove it's pure? Well, this one is a lot easier to prove. That's pure quartz. It doesn't look like there's anything else in there. And so, so we're going to try this. We're going to try to regrow the crystals. The important point about regrowing these crystals is you want to minimize nucleation. You don't want a whole bunch of baby crystals, because the baby crystals don't grow very big. What you want is you want a few crystals to nucleate, and those crystals you want to grow big.
Why is it that gold dust is more favorable because it's more pure? Well, like, I'm trying to say, like, gold dust is more pure, right?
No, it's because it's mechanical. Like usually when they get the gold, like gold nuggets and gold dust, like they're panning for gold, it's because of mechanical action in the river. They're panning, let's say they're panning the river. But originally they'll have gold. Have you seen a gold crystal? These are gold crystals here. Do you see that? When you see gold crystals, you see the faces and the features and the structure there. And those gold crystals get crushed up. But when they get crushed up, other things can get crushed up with it. And so you don't necessarily know. Maybe there's some other stuff that gets in there. Here, it's clear to see that there's some quartz. You see there's some quartz crystals there intergrown with the gold, but clearly the gold crystals are different than the quartz crystals, and the gold crystals are pure and the quartz crystals are fairly pure. And this is good purity stuff. When you see crystals like that, then you know, but if you were to crush it up, could you tell? There might be a little bit of quartz in my gold. It's hard to tell when it's like a little powder, and so that's the same thing with us. We want to see crystals. Some people grow really nice, beautiful gold crystals. This one is $4,420, but yeah, that's pretty interesting. But this is what they look like under a microscope. Well, this is probably not even under a microscope, but do you see that? That's gold, and that's pure. You aren't going to expect much silver. This is not like 18 karat gold, or this is like 24 karat gold, or 16 karat or 12 karat. It's pure, right? Although, the silver's tricky because silver can substitute in the same sites.
So that's made in the lab, right?
This? No, these can be found in certain deposits. And then in the rivers, then they get torn apart, broken apart into little flakes and pieces. But it depends on, there's these, under certain conditions, then you can have crystals like this grow. In these certain conditions, there's some kind of molten, under pressure, etc., and the gold precipitates out. That's what we're trying to do. We're trying to get our crystals to precipitate out like this, But this only happens under, certain conditions. It's of a quartz melt, and it's very molten. Everything was at one time. This could be man-made, though. Yeah, it could be. Rubies or synthetic diamonds, synthetic, a whole bunch of stuff you make in the laboratory.
Could you provide any insight as to why bismuth crystallizes the way it does?
Insight, I don't know why it crystallizes. It has to do with how the atoms pack together. I mean, bismuth is wild. Have you guys seen bismuth
It's not
crystals?
elements.
Yeah. It forms beautiful crystals. And it's just the way it packs together. But it's just the way that it packs together in nature. But why it forms like these, and why it packs together like that? You think it has to do with something with the size and other stuff, but it's weird. Certain things are a little easier, like sodium chloride, packs together in little cubes. You look at a salt crystal, it's just a cube. But this thing is pretty wild. I think people have probably studied it before, but I'm not exactly sure.
So that forms naturally?
Hmm?
That pattern forms naturally?
Yeah, this is natural. I mean, you just let it grow, and it grows like this into these types of structures. You can buy this stuff. You melt it in a pan, and then you just melt it and grow new crystals each time you can recrystallize this over and over again and form different, structures. So it looks architectural. It's pretty cool. Well, your crystals aren't going to look like this, but let's see what they look like. Mm. Hopefully we can get some nice crystals.
$50 for that? I think I get that on
Oh, it's handmade. Wonder how big it is. Oh, it's pretty big.
There's a YouTube video channel, I think it was Nile Red. He purified some bismuth crystals from Pepto-Bismol.
Oh, yeah. Oh, that's pretty cool. Yeah, you can make this. You can buy bismuth, chunks of it, melt it yourself and grow crystals. But our challenge is we need to grow crystals of the stuff we have. So let's see if you have any crystals there, and if you do, just keep letting them grow. If you don't, then we're going to start over again. We're going to start over and try to make some baby crystals, and then when we make the baby crystals, we don't want to make too many. So what we're going to do is we're going to dissolve the crystals and then pour. We just want liquid. We're going to pour it into a clean beaker and then try to nucleate it from that. And the more dust and more garbage in there, the more crystals you're going to nucleate. All right, I'm going to stop here. And then you're going to do is this. One, you have to prove to somebody what you synthesized is of high purity. And the way we're going to prove that is nice big crystals. Two, you have to prove to somebody that what you synthesized is what you think you synthesized. What did you think you synthesized? And if somebody argues that they don't believe you, how can you convince them that you synthesized what you think you synthesized? In other words, what is this stuff supposed to be, and then how can you prove that it is? Well, normally what we do is we do all kinds of analysis. We try to figure out the structure and the composition of this. But we don't have a lot of these analytical tools, so you're going to have to, well, fortunately somebody's already studied these. And so what you're going to have to do is you're going to have to compare your stuff to the stuff that's already been studied. Is it the same? And so in order to do that, you're going to have to do some research online to see what are the properties of the stuff you think you synthesized, and do they match? And I think that's as best as we're going to get. So we're going to use chemical arguments to convince the reader that we've synthesized the stuff and it has high purity. And the reader is very skeptical. The reader may not believe you at all, because that's what most scientists do. They want to see a lot of supporting evidence.